Hey everyone, my name is Jimmy. I'm a former LinkedIn software engineer who has spent the last 3 years helping others prepare for the coding interview. In this video, I'm going to be talking about depth-first search and recursion. We're going to learn how to use depth-first search and recursion to solve questions related to binary trees. Now, when it comes to the coding interview, depth-first search and recursion are arguably the two most important topics out there. And that's because they're very versatile. Aside from binary trees, they can also be used to solve questions involving graphs, backtracking, and dynamic programming. So this video is intended for anyone who's maybe just starting out in their studying journey, or for those who are comfortable tackling questions in that easy to medium range, but really just want to build a strong foundation so that they have more confidence solving problems moving forward. So we're going to first touch on how to use depth-first search to traverse the nodes in a binary tree. But the main focus of this video will be about recursion and how to use recursion to solve binary tree questions. So we'll learn about the relationship between depth-first search and recursion. We'll learn about how to think recursively when solving binary tree problems. And finally, we'll learn how to take that thinking and translate that into a working recursive implementation. So there is a text version of this material at the Hello Interview website. I'm going to leave all links in the description below. There you'll find free interactive visual guides to the most important coding interview patterns. And more importantly, I'll leave a couple of links to practice problems that you can try for yourself to apply what you learned in this video. Lastly, before we get started, please don't hesitate to like, comment, and subscribe, especially if you want to see more of this material in the future. All right, so let's get started. Depth-first search is an algorithm for visiting every node in a tree or graph-like data structure. It does so in a very specific fashion, which is what we're going to visualize now. So depth-first search is going to start at the root node of our binary tree. Then it's going to visit nodes by going down and to the left until we reach a leaf node, which is a dead end. Now at this leaf node, since we can't go down any further, what we're going to do is we're going to backtrack back up to the previous node. So this backtracking is a key part of the depth-first search algorithm, and it ensures that we can visit every node in our binary tree. But I also want to point out another fact is that when we backtrack away from a node in our binary tree, we've actually explored all of the nodes in the subtree rooted at that node. So we've explored all of the nodes at the subtree rooted at 1 when we backtracked away from it and went back to node 2. And this fact plays a key role when we solve questions using recursion, as we're going to see in a little bit. But from now, we can continue the depth-first search process. So at node 2, we're going to now visit node 3. Node 3, we reached a dead end, so we're going to backtrack back up to node 2. At node 2, we finished visiting both of its left and right children, so we're going to backtrack back up to node 4. And notice how after we've done that backtracking, we've finished visiting all of the nodes in this left subtree, which I've just shown by putting those nodes in dark blue. So at node 4, we're just going to now move on to the right. And here we've reached a leaf node, so we're going to backtrack. And when we finally reach node 4 again, which is our root, we've now visited every single node in our binary tree, and our depth-first search algorithm has finished. So we can think of depth-first search as a form of iteration. And we can use iteration to solve a question like finding the sum of the nodes in a binary tree. So what we'll do is we'll keep a running counter right here, sum, and then we'll use depth-first search to iterate over every single node in the binary tree. And when we reach a node, we're going to add that node's value to the sum. And when the depth-first search eventually finishes and visits every single node, we're going to have the sum of our binary tree at the end. So I'm going to refer to this approach as the pure DFS approach to finding the sum of a binary tree. It works perfectly fine. There's nothing wrong with it. But now I want to shift gears a little bit and talk about the recursive approach to the same question. And we'll dig into why and the advantages of the recursive approach in just a little bit. But first, we're going to talk about the how. So to solve this question of finding the sum of the nodes in a binary tree using recursion, we're going to need a different approach. And our approach is going to look like this. We're going to pick a node in our binary tree. Let's just pick the root node for now. And we're going to think in terms of this node's left and right subtrees. So here's the left subtree and here's the right subtree. If we know the sum of the left subtree, 2 plus 3 plus 1, which is 6, and we know the sum of the right subtree, 7 plus 5, which is 12, Well, we can use those two values, we can add them together, plus the sum of our own node, which is 4. We can add them all together to get 22, which is the sum of this entire binary tree. Now, the nice thing about describing the sum of a tree like this is that it can be applied to any subtree in our binary tree. So if we look at this left subtree right here, we're going to pick this node 2 as the root. Its left subtree has sum 1. Its right subtree has sum 3. Now 1 plus 3 plus 2 is going to give us 6, which then in turn can be used to find the sum of the entire subtree like we just saw. Same thing with this subtree right here. Its left subtree has sum 0, right subtree has sum 5. 5 plus 7 plus 0 is going to give us 12, which again is part of the sum of the entire subtree. So if I were to write an equation to describe what we just saw, it would look something like this. Sum of a node equal to sum of its left subtree plus the sum of its right subtree plus the value of its node. Some node just represents the sum of any subtree rooted at a particular node equal to the sum of its left subtree plus the sum of its right subtree plus the value of its node itself. So the one thing we do have to be careful of when we're using this equation is that for an empty subtree like the one right here, this actually won't apply. This is because an empty subtree has no left and right subtrees, so we can't actually use this equation to find its sum. An empty subtree is the base case for our recursion, meaning we can calculate its sum directly, and this is because we know that an empty subtree has a sum of 0 because it has no nodes. So these two equations can be used to find the sum of any subtree in a binary tree. So now let's actually visualize how the recursive solution to this problem works in code. This is also going to allow us to make the connection between our recursive solution and the depth-first search process that we covered in the beginning of this video. So on our left here, we have the recursive solution to our problem. Let's just take a moment to understand what this function represents. We have treeSum takes in a value node, and what it's going to return is the sum of the subtree rooted at the given node. Okay, and it's going to do that recursively. The first two lines represent the base case. The sum of an empty subtree is 0, while these three lines represent the recursive way of finding it in terms of its left and right subtrees. So now we're going to visualize each step of how this recursive function works. So initially it's called with node 4, and when this function eventually returns, it's going to return with 22 as the sum of this entire tree right here. So the first step of this function is to say, okay, in order to find the sum of my tree, I need to first know the sum of my left subtree. So we're going to do that by going in and making a recursive call to treeSum on node.left. So when we make that recursive call, what we're doing is we're taking a copy of the recursive function and we're pushing it onto the call stack, which is shown right here. So it's important to note that when this function eventually returns, it's going to return with the sum of this subtree, which is 6. So in order to find the sum of this subtree, we need to follow that same process. We need to first find the sum of the left subtree. So we're going to do that by making a recursive call. Now node is equal to 1 in this case. And if you notice, this is just the DFS process that we talked about in the very beginning of this video. So here, okay, node 1 needs the sum of its left subtree. Just going to make a recursive call to find that. And here we've reached our first base case. So now node is none. So this is going to hit this base case right here. So we can return 0 directly. It's really important to understand where this return value goes and what it represents. So we're going to return 0. And now this value gets returned to the node 1 as the sum of node 1's left subtree. So we have that value right here. And this was just the backtracking portion of DFS. So now node 1 has this value of 0 for its left subtree. So it's going to say, okay, let me go find the sum of my right subtree. So it's going to do that by making a recursive call. Node is none here, so we can return 0 directly. Okay, at this point, node 1 has a sum of both of its left and right subtrees. So now we're going to take those two values, add it to its own value, and return it back to node 2. Okay, so 0 plus 1. The sum of this subtree is 1. Now node 2 receives that value as a sum of its left subtree, and now it's going to go on and make a recursive call to find the sum of its right subtree. Okay, this just looks a lot like what we just covered, hitting the base case, hitting the base case, Okay, so now node 3 has the sum of its left and right subtrees, which is 0. It's going to take 0 plus 0, add it to 3. Okay, so now that 3 gets returned in the backtracking step to node 2. Node 2 now has the sum of its left and right subtrees, 1 and 3. So it's going to take 1 and 3, add it to its own value, and return that back up to its parent, which is node 4. So remember how I said when DFS backtracks away from a node, it means we finished visiting all of the nodes in the subtree rooted at that node. And so here's just a perfect place to visualize how that is important for the recursive solution. At this point, we've backtracked away from node 2, which means we finished visiting all of the nodes in this subtree, which also means we have the sum of that subtree. So that sum is the value that we backtrack with back up to node 4. Now, while the rest of the animation plays out, let's just recap the connection between DFS and recursion. So we use recursion to describe the sum of a binary tree in terms of its left and right subtrees, and DFS just controls the order in which we visit those subtrees to supply the relevant sums. And before we move on, let's just talk about the time and space complexity of this function. The time complexity is going to be O of n, where n is the number of nodes in our binary tree. And that's because we visit every single node once, and in each node, we're doing a constant amount of work. Now, when we talk about the space complexity, this visual is actually going to help us understand that as well. The space complexity is O of h, where h is the height of the binary tree. And if we want to visualize what that looks like, we can go to right here in our function's execution. You'll notice that there are a total of 4 calls on the call stack. We have to account for the space that each of these calls takes on the call stack. And that just corresponds to the height of this binary tree right here, the 4 nodes that we have starting from the root down to this node right here. So now let's talk about why we want to use recursion when solving binary tree problems. In general, there are 2 advantages for using recursion. The first is that it lets us solve a specific type of problem much more naturally and easier than other approaches. We're going to cover what those problems are in the next video, so don't forget to subscribe if you don't want to miss out on that. But the second reason is really for ease of implementation. On the left, we have the recursive approach to our tree sum problem, and on our right, we have 2 different versions of the pure DFS approach to the tree sum problem that we talked about in the beginning. In either case, the recursive version is just much fewer lines of code. In this version, we're using recursion to implement DFS, but we have to introduce a global variable to repeatedly add to it in each call. In this version, we're using an iterative version of DFS. It's going to be beyond the scope of the video, so I don't want to get too much into it. But this avoids having to use that global variable, but we are writing a lot more lines of code. And so aside from this brevity, once we've figured out how to think recursively about a binary tree problem, there's a very, very straightforward process that we can take to go from that recursive way of thinking about solving the problem to the actual implementation. We're going to cover that next. So what we're going to do now is we're going to write a recursive solution to counting the number of nodes in a binary tree. And we're going to do that by following the 5 steps that we laid out here, which is going to start with how to think about the problem recursively, then how to take that thinking and turn that into a working recursive solution. So let's just look at this binary tree right here. So if we're thinking recursively, what I'd like to do is I like to pick a node in the tree and then ask myself, okay, what do I need from my left and right subtrees in order to solve my problem? Remember, I'm trying to count the number of nodes in this tree. Okay, so if I know that there are 3 nodes in my left subtree, 1, 2, 3, and I know that there are 2 nodes in my right subtree, well, I can just take those 2 values and add 1 for my node to get 1 plus 2 plus 3 for a total of 6. Each function call is going to return the number of nodes in the subtree rooted at the given node. So it returns number of nodes in the subtree rooted at node. And having this clear definition of what each function call is going to return is important because it allows us to specify the base case correctly, which is step 3. So our base case, okay, if each call returns a number of nodes in the subtree rooted at node, if node is empty, so if not node, then we want to return 0 because there are no nodes in an empty subtree. Okay, so after that's done, we can actually move on to making the recursive call. So this is step 4. So I'm going to make recursive calls to node.left and node.right. And then I'm going to use those values in the return statement based on the way that we broke things down in step 1. So we can return left plus right plus 1. Now I just want to use the same process to show how to write a recursive solution to a slightly more complicated question. In this question, I'm writing a recursive solution to check if a target exists within a given binary tree. So if I have this binary tree right here and my target is 2, then that's going to return true because 2 is right here. But if I was searching for the target 8, I would return false. So again, just going to use these 5 steps to go from the way that I think about this problem recursively to the actual implementation. Okay, so first step is to think recursively. Again, I'm going to pick a node, then ask myself, what do I need from my left and right subtrees in order to solve my problem? Well, for this problem, I'm going to need to know if the target exists in my left or right subtrees, because if either of those things are true, then that means the target exists in my entire binary tree, right? If 2 exists in this left subtree, that means 2 exists in this entire tree. So once I've made that observation, I can clearly define what each function is going to return. So I'm just going to write that here. Returns if the target exists in the subtree rooted at the given node. Again, having a clear definition is really going to help keep my base case correct. My base case, I'm thinking empty tree. So if node is none, I'm going to return false because a target cannot exist in a empty tree. But based on this definition, we also need some more information that we can't just get through the recursive calls. So let's say we're searching for the target 4 in this tree and we're at this node. Well, 4 doesn't exist in our left subtree, 4 doesn't exist in our right subtree, so those recursive calls would return false. But our node is actually equal to the target. So we also need to check if our node is equal to the target, then we can just return true right away. So I'm going to do that now in the code. And where this statement lies in relation to the recursive calls is really important, and we're going to see why in the next section. For now, I'm just going to finish writing this function. So if I know that my node doesn't equal the target, that means I need to check my left and right subtrees so I can move on to step 4 and 5, making the recursive calls and using them in the return statement. And for this particular question, we can actually just combine them together in the return statement for something like this. So we can return if the search target exists in the left subtree or the search target exists in the right subtree. So the last thing I want to do is just visualize how this function works for a few different cases when our target exists within the binary tree. And the reason for this is I'm just going to show something called early return. So here I've just written the same logic as we had before in just a slightly different way that makes it easier to tell exactly what is returning true. Okay, so for the first example, let's just look at the most trivial one when we're searching for this target 4 and it exists at the root of our binary tree. So in this case, node.val is going to equal to our target, and we can just return true right away without having to make any recursive calls at all. But let's look at a slightly more interesting example, which is when our target exists in our left subtree when we're searching for the target 1. Okay, so let's see what happens. So first thing to check, node.val is equal to target. That's not true, so we need to go search our left subtree. So we're searching our left subtree by making a recursive call. Now node is equal to 2. Now we're searching for the target within this subtree. So again, we're going to make that recursive call because 2 is not equal to 4. Sorry, 2 is not equal to 1. So we're going to make that recursive call to our left subtree. So at this point, we're searching for if the target 1 exists within this subtree right here. So we're going to see that node.val is equal to target, so we can just return true. So this true value gets received by the parent of node 1, which is node 2, and it just indicates that, hey, that target 1 exists somewhere in node 2's left subtree. So this is going to evaluate to true, so now we can return true directly without having to explore any parts of the right subtree, which is what this code is doing. So we're going to see we're going to skip this recursive call and just return true directly. So we return true to our parent. So what we did is when we were right there, we basically said, okay, our target exists in my left subtree, so I don't even need to check anything in my right subtree. And you can imagine that if there are a lot of nodes coming out here in that right subtree, then this would be a very useful optimization that we could make. Now, the root node originally, which is node 4, it received this value as true. So it can just return true, saying that we found 1 somewhere in this binary tree. So this is going to be it for this video, and we've covered a lot. We've covered the basics of depth-first search. We've covered how to approach using recursion to solve binary tree problems, and we've learned how to take that recursive approach and translate that directly into code. And we've also visualized how recursive functions work and how that they can do things such as early returns. And recursion is always tricky for those who are just starting with it because there's so much happening behind the scenes. But hopefully this video helped spell exactly what each of those steps are, and you'll just get more and more familiar with them as you practice. So the most important thing after watching this video is to make sure you tackle some problems on your own. I've left the links to the relevant questions on hellointerview.com in the description below. Each of these questions is going to have detailed solutions that use a lot of visuals and follow the same step-by-step process that we talked about in this video. So by practicing doing them, you'll make sure you get the repetition that you need to really understand these concepts. And if you like this video, be sure to subscribe so you don't miss out on the next one, in which we further our understanding of recursion when it comes to binary trees by talking about when to use helper functions, when to use global variables, and the types of questions that are best solved by using recursion. Okay, so I hope this helps everybody in their journey. Good luck on your interviews, and I'll see you next time.